Hello everyone, and welcome to the first appendix to the Building Design Fundamentals video series. Today we're going to talk about how to create object types for walls. We'll start by creating new content. Right-click on the wall to make sure that you're setting attributes on creation. Click on the wall, and now we can change the name in the Properties tab and make sure that we're creating a 3D part with this new object. We need to make a couple of modifications straight away. First, we're going to double check and make sure that this is a product and not a part. We check that by right-clicking, going to Insert. We see that we cannot insert a product, so we need to go to the Tools toolbar, change the part to the product, and that will make the modification so that we're now able to insert products and parts into this product. Next, we're going to override our ambience to make sure that the ground is hidden because that's a little distracting. And we'll make a couple of geometrical sets. The first one will be input construction, and then we're going to make a second one, and that's going to be just our inputs. We're going to create a UDF to begin with, and this UDF is going to be instantiated automatically with component-based design when we assign the UDF to the object type and that object type to the wall feature. UDFs are a very powerful concept in CATIA. They're similar to power copies as they are parametric components that encapsulate parametric geometry that can be reused then across different models. We'll start with the inputs. These two lines are going to be the support of a mid-surface. When we're creating a wall object type that is compatible with the new building features in Building 3D Design, they can take a mid-surface as an input, an envelope surface, or a wall body. Here we're going to use just the mid-surface. If you'd like more information on what those inputs are and how they're used, go to our wiki page on our Buildings and Infrastructure SWIM community. For this UDF, our mid-surface is going to be an extruded surface between two planes. It doesn't matter that this surface is floating in the air because it's going to be replaced when we instantiate the UDF into our model, because Building 3D Design is going to automatically create a mid-surface for us that's extracted from the wall when we associate the object type to that wall. Next, in the input construction geometrical set, I'm going to create a wall. This wall is just going to be a visual reference to see that the UDF I model is more or less aligned with the wall geometry that I would be extracting this from. It's serving as nothing more than a visual reference, and I'm going to delete it later. We'll make another geometrical set. This is where we're going to model the geometry for our UDF, and I'm going to reorder the tree to make sure that things are in the correct order because it's my best practice. We'll call this geometrical set UDF 3-layer panel wall because the UDF that we're going to be modeling is going to be subdivided into panels. We need to make a wall thickness parameter. We'll do this in the parameter set, and then we're going to copy that parameter set and paste it into the geometrical set that's going to host our UDF. We'll delete the original one we just created. We'll go back to the parameters that we pasted into our UDF geometrical set, and we'll rename those control parameters. These parameters will be exposed by the UDF. Also, it's essential that this parameter is named wall thickness with the capital W and capital T because Building 3D Design will set this value when we instantiate the UDF into our model. Another parameter that we're going to make here is wall covering thickness because this is going to be a 3-layer wall that we're going to model, and that parameter will then drive the thickness of our wall coverings. So to start modeling our UDF, we'll make a thick surface. We're going to select the mid-surface as an input, and then we're going to create two formulas to control the thickness of this surface so that when we change the parameter, the thickness of this thick surface, or thick volume rather, will update. We create these formulas by right-clicking in the offset field, and then we can simply click the parameter that we want to use, add any mathematical equations to that, and then commit by clicking OK. We'll do that to both offset values. Within the Edit Formula window, you can actually create some very powerful equations. So go ahead and explore the language browser and you'll be able to see some of the capabilities you have within that Edit Formula dialog box. And now we're going to make our first covering. This is going to be offset from the same mid-surface. And now we're going to do some mathematical juggling with the different parameters to make sure that the thickness of this surface is offset somewhat from the mid-surface. In order to do that, we're going to play with the formulas to set the correct values to make sure that this isn't really a thick surface. This is going to be an offset thick surface. We'll test this. Does it look right? No, it's incorrect. So let's go back to the formula dialog box and edit it. Let's make it minus wall thickness divided by 2 plus the covering thickness. And that's going to give us the proper location of this wall covering. There, those are good, minus 90 and 100. We'll rename this volume wall finish 01. And now, rather than model it again, we're just going to copy it. We'll paste it, and then we'll edit that feature and swap the direction. That way we don't have to go through and recreate those formulas. And the formulas will be automatically created for us. And then we'll rename it wall finish 2. And just like that, we have 3 wall volumes that represent the 3 layers of this wall. And they're all inside of our UDF geometrical set so that we can easily create the UDF from this geometrical set. And we'll verify that the geometry is correct, which means that our formulas are correct. And when we change the parameters, we see the thickness of the wall coverings update. And we'll do a double check here to make sure that the thickness of the core is updating as well, and it's the correct dimension. And a last check. This is good. This is a 200 millimeter wall. So we're all set. We'll play with the parameters a little bit, make sure that it's all good to go. And then these parameters, when we create our UDF, will be exposed and accessible from our wall when we instantiate it into our model. The next step is to change the graphical properties for these features. We'll give them a color that is representative of the material that they represent. We could add a material to this as well, so that within live rendering we could create lifelike rendering, but we're going to skip that step for now. Next, we need to look at the relations. In order for this UDF to maintain its parametric relationships between the formulas and the geometry, especially those volumes, we need to move the relations from the exterior of that geometrical set into the interior. We'll do that by copying the entire relations set, pasting it into the geometrical set, deleting the original relations, and then activating the duplicate relations, those duplicate formulas. And by doing that sequence of operations exactly in that sequence, we'll be able to maintain the formula relationships between the parameters and the geometry. So with that done, we're good to go. Our UDF is essentially finished, and we'll test it to make sure that the parametric relationships are all good. Remember that arc we created in the sketch? Well, we're going to use the replace command to move all of the geometry from our UDF geometrical set from the line to the arc to make sure that the wall, when it's instantiated into our model, will be able to adapt to any geometry that that wall has taken on. This is another reason why we've used the thick surface command and not an extrude or a pad. We can make our UDF now. We'll go to the Tools tab, and where we can create a power copy or UDF, we select the UDF command. We select then the geometrical set where we modeled everything. You see that the input is the mid surface. That's great, and the name needs to be identical to what you see on the screen. We'll give the UDF a name, and we're going to expose the parameter wall thickness. That way Building 3D Design will recognize that parameter and it can set it for us when it instantiates. And we'll also check the outputs to make sure that our main result and our finished surfaces are correctly exposed. Click OK. And we have a knowledge templates node in our tree now with the UDF visible, and we see that the parameter is set and our wall finishes are there. Let's save. The next step in creating our object type of our wall is to build the detailed wall assembly that will then be inserted into an engineering template. In order to do this, we're going to add 3 new products. The first one is going to be an AEC structural element. Remember, right-click on that when you're creating the new content or inserting the extended product. That way you can make sure that you're going to create a 3D shape when you're creating the new object. The next 2 are going to be coverings, and those are going to represent the finished surfaces or finished volumes of our panel wall. So let's create 2 of those. We'll name the first one 3-layer panel wall covering 1, and the second one will be 3-layer panel wall covering 2. And those will consume the volumes that we just created, and we're going to add a bit more detail to them to panelize these parts in a way that we couldn't do with the UDF. We're going to check to make sure that these are actually products. We do that by right-clicking, going to insert, and seeing if we can insert parts or products into them. We can't here, so we need to again do the same thing we did at the beginning. We need to switch these parts to products. We do that in the Tools tab of the Building and Civil Assemblies application. It's hidden. You need to make sure that you're able to navigate to that in the tree. And now everything is good. These are products. We can add parts and products to them. Let's go into our first core part, and let's change the geometrical set to wall core. We're going to panelize the core and the finishes using the multi-split command. And in order to drive the dimension of those panels, we're going to create a new parameter inside of our UDF, and we're going to call this wall panel width. We're going to set this parameter to 2 meters for now. We'll give it a name. We'll call this wall panel width, and then we'll make sure that this gets included in our UDF in a little bit. Next, we need to create some stable geometry that will act as a support for the dividing of our multi-split to create the panels. We'll do that first by creating an extremum from the XY plane of the mid-surface, and then we're going to make a plane that is the offset of the XY plane, and we're going to make another formula to make sure that this plane always sits 10 centimeters from the top of the wall, 10 centimeters from the extremum. I know the syntax for the distance function by heart, but if you need a little help, use the dictionary to navigate to this method, and you can find all of the information you need to create this distance formula there. We're doing that so that if we place a door or a window on this wall, ideally the intersection of this plane and the mid-surface will not also intersect the door opening or the window opening and make it disconnects. So we create an intersection with the new plane that is 10 centimeters from the top of the wall and the mid-surface. We're going to name that divide line, and we'll use this as a division curve for our multi-split. You'll notice I'm being very particular with the naming so that it's easy to track geometry and follow along the geometric dependencies from one part to the other. We go back into our wall core part now, and we're going to create the multi-split. It's in the Develop tab of Building 3D Design. We'll select our wall core volume from our UDF, and the command is automatically going to create an extracted geometry of that volume. We don't want that. We want to use the divide line. If we use that extract geometry, it's going to cause problems when we insert our engineering template. So make sure you edit the pattern, select the divide line, change the value to 2 meters, and we're also going to do something here. We're going to set the results of an output from this multi-split as a structural element. Once you've committed that, go back and delete the extract. You have to delete the extract. That's essential, otherwise you're going to get issues. And now we're going to link the division of this pattern to the parameter that we just created, wall panel width. We have to do this a different way. We have to click on the Formulas tab in the Tools toolbar, navigate to the value that sets the division, edit formula or create formula, and then go up and click on the wall panel width parameter from our UDF. It's going to create an external parameter for us, and the divisions now will be driven by that parameter. We're going to do the exact same thing now for those 2 wall covering volumes. So let's go to the next 3-layer panel wall covering 1 part. We'll change the geometrical set name. We'll create a multi-split. We'll select the first wall finish volume. We'll set the value of the divisions, and we're going to change that pattern and modify it. We're going to not use the extract. We're going to use the divide line that we just created. We'll make sure that we're outputting from this multi-split geometric components that are of type covering, and you'll see why this is important later on. And then we delete the extract. Remember to delete the extract. If you want, we can change the color here. We could add materials to this, but we're going to skip that step for now and just do coloring. And again, we're going to make sure that this wall is divided by a dimension that is equal to the parameter wall panel width. So again, click on the function button in the Tools toolbar, add a formula to the value that sets the divisions of this wall, and make sure it's linked to the wall panel width parameter. We'll do this one last time to wall finish 2. We'll click on the multi-split. Let's select our wall finish 2. We'll change the spacing to 2 meters. Let's edit the pattern. Click on the divide line instead of the extract. Click OK. Make sure that these are outputting coverings. Delete the extract. Go to Tools, click on the Functions button. Navigate to the value, add formula, click on the parameter, click OK, and OK. And now everything is linked parametrically to the parameters that you defined in your UDF. And if you like now, we can flex these parameters and make sure that our wall is parametrically updating. So we click on our wall panel width parameter. Let's change this to 4 meters and see how it updates. Run an update. And this is good. This works on our finishes. Let's set this to 1500 millimeters, see how that works. Run an update. You can see now that because we created those formulas, all of the features in the multi-split are associated to that parameter. And we've got a strong parametric model here. We need to add the wall covering thickness to our UDF, and we also need to add the wall panel width parameter to our UDF. You see the wall panel width isn't showing up yet because we need to change and update the components of our UDF definition because that parameter came after our initial creation of the UDF. So don't forget that is an important step. If you make changes within the UDF geometrical set, the definition won't update by itself. You need to manually make sure that the definition is updated. Finally, this is a pretty important step. It's not going to impact the process today, but it could if you're using component-based design in a more classical sense. You need to make sure that your wall object type and engineering template have a base axis system that acts as an anchor when you're using the define component specifications command with component-based design. But for building 3D design and the implementation of component-based design for these walls, that's not going to be an essential step. We're just going to do it anyway. This concludes the modeling operations for our detailed panel wall assembly. We could do this with the building designer role. For the following steps, when we create our engineering template, we're going to need to switch to the building design engineer role. Next up, we're going to capture this assembly as an engineering template so that it can be instantiated into multiple models and duplicate all of this parametric geometry. So create an engineering template. We're going to add that assembly into our components to process and make sure that they are all set to duplicate. Then we need to add the input, and that input is going to be the mid surface. We'll select that from our inputs geometrical set in our model context. Click OK. That's great. We have our mid surface. We also need to make sure that the parameters that we set in our UDF are also set as parameters in our engineering template. So go to the parameters tab, find those 3 parameters, wall covering thickness, wall panel width, wall thickness. It can be difficult to find in that list of parameters, but it's essential that you do it. Click OK. Change the engineering template name, and again, I'm trying to be consistent with the names. My assembly was called ET Engineering Template UDF User Defined Feature, and my engineering template is then just going to be ET Engineering Template. After creating the UDF and creating the engineering template, we can create our object type finally. So create new content, search for wall, click on the object type option this time. We'll give it a name. Again, naming is important. And we're going to make this one adaptive. There's additional options to add more information if you want to, but we're going to keep it simple and skip that for now. An object type is really just a resource table. A resource table that groups user-defined features, power copies, and engineering templates into the same context. It's really nice to have these parts open on the side so that you can quickly select them. So let's go to the UDF, let's set the UDF, let's change the tab, find the UDF that we had just previously modeled and add that as the UDF field. The engineering template is the same. We set the engineering template, navigate to that window, click on the engineering template, and it will fill that field in our resource table. If these models weren't open, we also could have searched for them in the database. Now save the object type. Finally, remember we created a wall in our UDF to visually validate the design of our UDF. We don't need that anymore. We're going to delete it to make sure that we don't instantiate it when we instantiate our engineering template. So let's navigate there. Let's delete that wall because everything inside this assembly is going to be instantiated and we don't need that duplicate wall. And be sure to save this assembly in this state, because it's the latest saved version that's going to be instantiated. At this point, the hard work is done and we're just going to instantiate our object type. The following steps have already been covered in previous videos, but we're going to run through it here so you see how it works with our newly created object types. We'll distribute our concept walls into a new part in our detailed design model. We'll call these panel walls, just simply, and we'll place these walls inside our architectural model. Why not? This is level 10, this is our penthouse. We're going to do this with traceability and associativity as parametric features. Click OK. Distribute has graciously created our new walls in this new part. Thank you so much. You can see the walls are in our geometrical set. What we're going to do is multi-edit all of these walls and search our database. We did not add these to a library. So we'll search the database. You can see that that wall has already showed up in our list of wall object types, and there we go. Wall covering thickness is exposed, and we can change that value here. Wall panel width is exposed, we can change that value here. Wall thickness is not exposed because it's been set automatically by Building 3D Design. And so if we changed any of the thickness of these walls, that would automatically change the thickness of the UDF that's instantiated. Let's take a quick look at what happens if we change the wall covering thickness. Let's take it from 15 millimeters to 20 millimeters, and you'll see all of the UDFs inside of the walls automatically update because Building 3D Design pushes the update to those features. Next, we're going to make sure that all of these walls have publications so that change LOD will instantiate our engineering templates. Changing level of development happens at the product level, so double click on your panel walls product. Select the walls that you want to instantiate and click OK. Make sure you're exposing the product and process. You'll follow along with the progress here. It goes pretty quick, and you can use multi-core processing to instantiate multiple engineering templates in parallel. Instantiating these templates this time did not automatically update all of my walls, so I'm going to right click, you see all of my assemblies are there, and do a local update to update the walls into the correct location. And there they are. Let's hide the 3D shapes so that we see just the assemblies that we instantiated. And I'm going to also change the visual settings to hide axis systems so that we're not distracted by those X, Y, and Z characters. To edit the values of, say, the panel width, you need to show the distributed walls, edit one of them by double clicking on it, change the panel width, and then run an update again. I'm going to do a local update. That, for some reason, didn't update the parameter inside the UDF of the wall that I instantiated. So I'm going to update that parameter and then local update the assembly, and you'll see now all of the panels inside have been updated. Let's open that assembly and take a closer look at what we have here. You do that by right-clicking on the product, go to the wall core, and open a new app. So you see, because of the way we modeled the UDF in the engineering template, even though there's a door in this wall, the wall was easily able to adapt to that geometry. And it looks like, based on what we modeled here, this looks like a pretty convincing CLT wall. So if we were to build a CLT model, cross-laminated timber, we could actually put a lot of information into this engineering template to represent all of the manufacturing requirements for this wall and build directly from this model. In building and civil assemblies, we can move the mannequin around to give us a better sense of scale, and also, if you like, you can change the referent. There's two available, two humans available. There's a gentleman and this Jane Doe. Let's go back to our model. Let's do this for the other wall as well. And again, we could change the values, the panel values for all of these, but we're just going to change the panels that have doors for the sake of this demonstration. Same process. We show the distributed walls. We change the value of the distributed wall. We run an update. That did not update inside of our panel wall assembly. So we'll manually update that parameter and then run a local update on that assembly, and you see that the panel widths have updated. Finally, you remember when we created our assembly using the multi-split, we set the specification for component-based design of those resulted split geometries as the types of features that we were instantiating. And we did that because they're recognized by component-based design. And when we use change LOD on the sub-assemblies, we get a further sub-assembly of these features as PLM objects. Now they are fully exposed. We have a fully detailed product structure, one PLM object per component, and this sub-assembly is visible then within the context of the subassembly itself or the larger project. So take note, the multi-split actually outputs specifications for component-based design. So you could attach object types that contain engineering templates to the specifications of multi-split, and using change LOD instantiate those engineering templates automatically. In practice, you're nesting object types inside of the other and using change LOD to automatically instantiate those engineering templates daisy-chained one after the other. There you have it, a crash course in creation of object types for walls or building 3D design. I hope you learned something. I hope you enjoyed it, and I look forward to seeing all the amazing things you're able to do with it.